hydrodynamics thing, we had a lot of discussion about this formula and what happens when the flow goes through orifice. And I introduced you to this Reynolds number. So that was the thing that we did last lecture. And now I will open a new PDF. So flow resistance. So flow resistance means that how much losses there are in a hydraulic system. And what kind of losses there are? Well, if there are no leakages, then the losses means that we lost some pressure. And there are three different main types of this pressure loss. It can happen in pipelines. It can happen when our flow needs to change the direction, which means the second point here, pressure loss through formed parts. And the third main type is pressure loss is what happens inside components, meaning that when the flow needs to go through some pneumatic, not pneumatic, but hydraulic component. And I can draw something for you. Just a moment. So the thing is that actually it is already there, but let's draw it again. So if we have a diagram and there is distance and there is pressure, and now with the distance I mean that how far away we are from hydraulic pump. And then I try to draw here a hydraulic circuit. At first we have a hydraulic pump, then we have some straight pipe, and our starting pressure, let's agree that it is over there. So that is our pressure 1, and it was taken from this point. And then when we have some line in hydraulics, because we have these losses in pipes, our pressure starts going down. And then if we face some junctions or such places where our flow needs to change accidentally a direction, for example, we might have this kind of thing over here for some reason that the pipe is not straight, but there are many junctions or it has to change direction. So what happens in the pressure? We have a sudden pressure drop which is larger than the drop in this pipeline in normal way. And then I think that there could be some sort of valve here. Some directional valve, no matter what it is. Then we see also a drop down. And finally, we reach the target, which was hydraulic cylinder here. And if we measure pressure at this point, let's call it P2. it would be in this level. So we would have this much pressure drop. So now the delta P is our pressure losses in system. And you can see three different reasons for this pressure loss. The reason one is the pressure loss in this pipeline. Then the reason two is this different formed parts. And the reason three is the components. So always in a hydraulic system, you have the highest possible pressure right after the hydraulic pump. And the more you go in hydraulic circuit, then the pressure will go down, 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 down. But still this pressure 2 is the one what we actually need to lift our load, for example, or do some work with this cylinder. So that's the reason that if you calculate that, for example, 100 bar pressure would be enough to lift certain load with the cylinder, then you you need to have higher value in your pressure relief valve because there are these losses in this system. Does it make sense?
Sorry, can you repeat that? I kind of missed that one because of my computer lags.
Okay, which part you missed? I was telling that we have three main types of losses, pressure losses, and okay, now your voice is circulating, or my voice is circulating somehow. I need to. Okay, thank you. So there was this, or there is, or there are these three main types of pressure losses: losses in pipelines, losses in these junctions when the pressure, the flow goes through formed paths, and then when we go through valves. And now let's have a look how to calculate, how to define these losses, and what are the most meaningful losses on the system. At first, the flow resistance in pipelines, pressure loss in pipeline. There is a formula how to calculate this loss, and it is here. So delta P is now the losses. Then there is lambda, which is called flow resistance value. Then there is L, which stands for length of the pipeline, and D is the diameter of the pipe, and ρ is density of the fluid, and this V is speed of the oil. So this is not the kinematic viscosity, but this is speed of the oil. But it is not that simple that you just put the values here. But first you need to define that what kind of flow you have. Do you have laminar flow or do you have turbulent flow? You remember from last week I told you these two flow types. If you have the laminar flow, which is the case that we would like to have every time, then it is relatively simple because then the lambda just gets value 75 divided by the Reynolds number that you calculated. But if the case is turbulent, then the resistance value lambda is a little bit more complicated to calculate or define. It's two different options. You might have hydraulically smooth pipes or hydraulically rough pipes. And if you have hydraulically smooth pipes, then you need to use this Blasius formula to define lambda. But if you have so-called hydraulically rough pipes, then you need to use Moody's formula or Moody's chart. This Moody's formula is not visible here, but the chart is, I think, in the next page, or then it was another link in Moodle. Let's see. Okay, I will show you this Moody's chart. It's here. No, there is some restrictions. Just a moment. I will fix them. Okay, now the Moody's chart is visible, and it looks like this. So down here is the Reynolds number with the logarithmic scale, and then the y-axis is the lambda, what we are looking for, and then here is K divided by D. That's a so-called relative surface roughness of the pipe, and the K stands for absolute roughness value, and the D is the diameter of the pipe. And when you know this information, and when you have calculated the Reynolds number in your case, you can see the point here where the Reynolds number and your this K divided by D curve will match, and then in that point you can see here in y-axis that what is your lambda value. Okay, this might sound a little bit complicated, so I try to tell it once more. Every time you want to calculate the flow resistance in pipeline, you use this formula here. It's the same formula for laminar case and turbulent case. But the lambda value depends the case, turbulent and laminar, and also it depends if you have a turbulent flow, that do you have hydraulically smooth pipes or hydraulically rough pipes. And this information, that do you have a smooth pipe or do you have a rough pipe, there are also some formulas available, or then this information can be told to you that you have hydraulically smooth pipes or hydraulically rough pipes. In laminar case, lambda is just simple this. In turbulent case, in the case of smooth pipes, you can use this formula. In the case of rough pipes, you need to find out the lambda value from the chart. Understandable or not?
Excuse me, I have questions. For the first value for the horizontal lines, why is 10 power of something? Can you?
You mean this one?
No, I mean the chart. Yes, and on the horizontal line in X axis.
Yeah.
For first, for the first,
Yeah, it's a little bit messy now, but it's 10 power of 2. So basically it is just a way to tell that it's equal to 100. And
seven.
there is 1000, 10 power of 3. So it means 1000. There is 2000, 3000, 4000, 5000, 6000, and there is 10,000. So this is a logarithmic scale. And maybe you remember that the critical Reynolds number that we used to compare things, it was this 2300, and you can see it roughly somewhere here. So basically this line kind of describes this laminar case. It is not this 75 divided by Reynolds, but it is in this case 64 divided by Reynolds. Sometimes you see a little bit different values because it's not exact value, but it depends on what kind of surface roughness you have in the pipes also here, but I don't want to confuse more about this, and that's why I just told you that the value 75 divided by Reynolds should be used if we have a laminar case. And this is a point that if we go on this side, then we have this turbulent case. If we stay here, we are in a laminar area.
Yes, thank you.
Yes, no problem. I just thinking that or checking that if there is more clear Moody's chart available, but yeah, because this is not so easy to read at the moment. But is the process other way understandable?
Yes, it is.
There are some tables that can show you that how much flow resistance you have in pipelines. For example, in this Festo Hydraulics book, you can see this kind of table. There are values from 6 millimeter pipes up to 60 millimeter pipe. And how to read this table, there is a speed of oil inside pipe starting from 0.5 meters per second, and the other end is 6 meters per second. And then what you can see here is the Reynolds number directly, the value for lambda, and delta P, the pressure drop in 1 meter length. And then there is two letters, K and W, and it means that you have the same oil with two different temperatures. And since the temperature is different, then the viscosity of the oil is also different. So the case says that the oil temperature is 15 degrees Celsius, and which gives, in that case, 100 square meters per second kinematic viscosity. And this W stands for 60 degrees Celsius oil, and the kinematic viscosity is only 20 square meters per second, square millimeters per second. And you see how much difference there is. In this case, 0.5 meters per second and 6 millimeter diameter pipe. If the oil is 15 degrees Celsius, the pressure drop is 0.44. But if the oil is 60 degrees Celsius, then it's only 0.09. So there is a huge effect that what is the viscosity, not necessarily the temperature, because there are different types of oil. Some of them have a different temperature in different, some of them have different viscosity in different temperatures. So that's not the point, the temperature itself, but the viscosity. That has a great effect to this pressure loss. And as you see, it would be beneficial to have as low viscosity as possible. But then there are some other problems if the viscosity is too low. There can be leakages and the hydraulic system won't operate proper way if the viscosity is too low. But the ideal range of viscosity is somewhere between, let's say, 20 and 40 square millimeters per second. So with this table, you see more or less the same things what you could calculate with this formula. Those values are coming from this formula. But I think that it is not so useful because you would need to have exactly certain values and certain diameters, and this is not the case. But you might have a different speeds, different diameters, different viscosities, and then there is no use for this table anymore.
Can I ask questions? Like
Yes, sure.
the viscosities depends on the fluid we use on the in the hydraulic system. I
Yes.
think with different fluid they have different viscosity.
Uh, there will be a lecture about hydraulic fluids later, but you can pretty much select the viscosity you want, or in a way that do you want to operate in a cold condition or are you operating in a warm condition. There are different oils or liquids for different temperatures, so that they give you those fluids that are meant to be used in a cold conditions. It means that the viscosity is low, even the temperature of the oil is very low. But then if you use such oil with high temperatures, then the viscosity goes too down and then cause problems. So that's why you need to have different oils for different operating temperatures.
So this table just gives an example about the pressure changes in just one fluid,
Yes,
isn't it?
just one fluid, and yeah, in real life you have huge amount of different fluids available. And then that how much the temperature is changing or how much the viscosity is changing when the temperature is changing, it is not constant, but it is also something that different oil types have different characteristics, and you can have some additives inside the hydraulic fluid so that the characteristic will become better. You call it viscosity index, that how much the temperature changes when the or how much viscosity changes when the temperature is changing. And of course, those oils that have a high viscosity index, they are more usable for different temperature, or they have a larger operating temperature area, but they are more expensive.
Yes.
One question, sorry.
Yes.
What it means the K or the W? I mean, what's the difference between this?
If you have a look at here, it says that the difference is that they have different viscosity.
Oh,
The
okay.
K has 100 and W has 20.
Okay, and they have different temperature, right?
Yes, yes. The idea is that it's the same oil in two different temperatures,
Okay.
and then you get different values for Reynolds number, for lambda, and for this pressure loss.
So when we look at the case, we just focus about the viscosity instead of the temperature, isn't it?
Yes, the viscosity is the main thing, not the temperature itself, because you need this viscosity when you calculate the Reynolds number, and the Reynolds number is the reason why you get different numbers in lambda and delta P.
Yes, it's clear now. Thank you.
Okay, but then it's your time to use this formula. So you should calculate flow resistance in pipeline in two different cases when the speed is zero point 0.5 meters per second and so that the speed of oil is 5 meters per second. And the pipe diameter is told, kinematic viscosity is told, density is here, and the length of pipe is 1 meter, and then it's told that the pipe is so-called smooth pipe. So take paper and calculator and try to solve this one. And I will give you time to solve it, and then I will show you the correct answer after a while. And if you have any questions that you want to ask here during your calculation, of course, you can do it. So the very first thing that you need to do is to find out that do you have a laminar flow or turbulent flow, and you need to use this Reynolds number formula to find that out. Okay, what is the situation? Do you think that I could show how to do it, or do you still want to take your time to try it yourself?
I think we can be ready.
Excuse
Yeah.
me. Excuse me.
Yes.
Uh,
Че?
how can we
Сейчас,
know?
сейчас напишу, я еще не все сделал.
How can we know the unit of that one? Because when I calculate, I just use meters and second and kilograms.
Че говоришь?
I didn't know how to change it into Pascal.
You don't need to change anything, but it automatically comes. And if you have a look how the Pascal will form, it is newtons divided by square meters. So you can tell it also with the help of kilograms and square meters or meters and such, but you just call it Pascal. So in a way, what Augusti is telling, it's correct, but about this unit, but you call it Pascal, and I think you should know it if the thing what you are calculating is called pressure loss, or you see this letter small p there, then what you get is pressure. And the SI unit for pressure is Pascal, so definitely that's the one what you get out of it if you put their SI units.
But when we consider the Pascal, we just consider newtons per meter square, and there's uh, second in the unit. So I didn't know where does this come from.
No, I don't fully understand what you mean, but let's have a look at this calculation now. I will try to explain it, and I hope this will also get some clarification at the same time. So I will make it on the paper. There, new sheet. So what was the values that were given? The diameter of the pipe was 60 millimeter, and then the density of the oil was 850 kilograms per cubic meters, and then length of the pipe was 1 meter, and the kinematic viscosity was 100 square millimeters per second, and then the speed in case A and in case B were different. So 0.5 meters per second and 5 meters per second. So this was the starting point. And at first, this flow type needs to be defined. And we can do it with the Reynolds number. It was this speed of the oil multiplied by diameter of the pipe divided by this kinematic viscosity. Okay. So in A, we put the values here. And now I told you that the Reynolds number doesn't have any units, but we need to be careful that we put here the similar units so that they can be simplified away. And now in the given values, there are millimeters and square millimeters per second, and then the speed is meter per second. So something we need to convert so that we have similar type of units. And I think in this case, the easiest would be to convert the speed so that it's not 0.5, but it is 500 millimeters per second. So I put here 500 millimeters per second multiplied by 60 millimeter. And then I can directly use this value for this kinematic viscosity, 100 square millimeters per second. And we see that those units are simplified away, and the result is 300. Okay, so now the Reynolds number is 300, and the 300 is smaller than this critical Reynolds number, which was 2300. So we know that flow is laminar. And when we know that flow is laminar, we know that we can use the lambda 75 divided by Reynolds. Okay, and then if we calculate this thing first for this stage B as well, so the Reynolds number, actually only thing what changes is the speed. It's not 500, but it's 5000. And we get 3000, which is larger than this Reynolds critical. So we know that the flow is turbulent. And then it was told that we have a smooth pipe, which means that we have to use this Palacios. So the lambda is 0.3164 multiplied by Reynolds number power of minus 0.25. Okay, and then we are able to solve the problem or get the final values. So delta P, the formula was this lambda multiplied by length of the pipe divided by diameter of the pipe multiplied by density of the oil divided by 2 multiplied by speed of the oil power of 2. And the lambda is 75 divided by 300. Then the length of the pipe is 1 meter divided by 0.06 meters. And density of the oil is 850 kilos per cubic meters divided by 2. And the speed of the oil, power of 2, 0.5 meters per second, power of 2. And what we get is roughly 443 pascals. So that was the case A. And then the B, we use exactly the same formula, but the lambda is defined in a different way. So now we put there this 0.3164 multiplied by 3000 power of minus 0.25 multiplied by these other values are the same. Except the speed, of course. Five meters per second, power of 2, and now the answer is 7,571 pascals. Okay. So, what do you think? Is it clear?
Yes, I see.
So at the moment, we see that our speed difference between the speed in A and B. In B, we have 10 times higher speed compared to A. But if we have a look at the pressure loss, it's more than 10 times. So when we stay in a laminar area, then our increase of the pressure loss is linear. But when we go to a turbulent area, then our pressure loss is going to increase more exponentially. That's the reason why this value is more than 10 times higher compared to this one.
So speaking about the units, does it mean that the final results we get in pascals, right? So we
Yes, the final result. Yeah. Go on.
Nothing. So we just leave it in pascals and do not convert into anything else.
In some cases, it might be necessary to convert it to bar, because it might be that those values, what you get out of the calculation are so big that it makes no sense to give them in pascals. But in this example, we got relatively easy situation. Our pipe length was only 1 meter, and we had a relatively big pipe. 60 millimeters is already a big pipe. So that's the reason why we got so small number here.
Okay, thank you.
So, for example, normally, which is the lossing rate in the hydraulic system? Can you talk more about that?
Yeah, normally, like I think in the quite early lectures, maybe in the first lecture, I told that the efficiency of the hydraulic system is not so good. It's something like 70%, and then you can say that it is an okay hydraulic system. And where does this loss come from? Well, the pressure losses of the system is the one reason, and then some friction losses in the cylinders and actuator is the one, and something comes from the pipe pump itself. But the most important thing is that you will always, when you design a hydraulic pipelines, you have to make the pipes so big that you will be in a laminar area. There are certain rules. I will show them later in this course, that what are, let's say, the suitable speeds inside hydraulic pipes, what can be used when dimensioning pipes. But now I just at the moment want to show how to do this calculation for the losses. And like you remember, this was the first stage of the losses, what kind of losses are in pipelines, and then we can have a look at the other loss types. So the other loss type is when the flow goes through these formed paths, and there is a different formula which actually looks pretty much the same that we used earlier, but we are only missing this length of the pipe divided by the diameter of the pipe, and we don't have lambda, but instead of lambda we have this other Greek alphabet called xi, and now the xi is form coefficient. And this is something that you have to read from some table, that how big is the form coefficient in different cases. This is just an example taken from this Festo book, that if you have, for example, this kind of a T piece, so that there is a flow coming and then the flow has to be splitted in two parts, then there is some losses, and the form coefficient factor is 1.3 in this kind of case. And then you would be able to find out that how much is the pressure loss in here. And in similar way, if you have this 90-degree bend or double angle or 90-degree angle or valve, there are values. But if you have a look at this 90-degree bend, you see that this table is not given exact value, but a range from 0.5 to 1. So it tells that if you want to, if you for some reason need to define this more accurate way, then there are other formulas how to calculate the xi value. It depends that what is the radius of this curve and what kind of surface roughness you have here, and then you are able to find out more accurately the value for this one, but we don't need that accurate information in this course. Because to be honest, the losses, what happens in these kind of places, they play not such a big role. More important is to understand the pipe losses and the losses what happens inside valves. So this is not a smart way to calculate valve losses, so that you just pick some number between 5 and 15 and then put it in this formula. Because the manufacturers will tell you more detailed way that how much losses are in valves.
Excuse me,
Yep.
So this number does this depends on the viscosities or the fluid flow through?
No. These numbers are not depending on viscosity. It's only what kind of shape there is and what kind of roughnesses there are and so on.
So it can be applied to every fluid, isn't it?
Well, yes, more or less.
Yes, thank you.
Okay, but then the final one, the third loss that I want to introduce you is that what kind of losses you have inside components. And mostly in hydraulics, the component that we are talking about is some kind of valve. It can be a directional valve or it can be some flow control valve or pressure control valve, but anyway, a valve. And these are in many cases such losses that have greatest effort. And the manufacturer, they give this kind of delta PQ characteristic curves of the valve. And if you know that how much is the flow rate that goes through a valve, you are able to read that how much pressure loss you have. And it's not in a way that the pressure loss would be the same no matter what road you go, but depending that is your flow going from P to A or from B to T or A to T or B to B, you have a little bit different curves. So you need to know the situation that you are studying to find out the accurate value that how much losses there is. But if you have a situation that you want to find out the total losses of the system, for instance, in a case that the cylinder is doing the extending motion, then the flow first goes from P to A and then to the cylinder, and then the returning oil comes back from B to T. So actually it happens two different losses in the same valve if you want to consider total losses of the system. And in this sheet, uh, well, basically I already told you this information, but in a visual way told here that what kind of losses there are in a hydraulic system in overall and how the efficiency is formed. So if you think that totally you have the maximum power put in the hydraulic system in here, 10% goes to pump, 10% goes to the valves and lines, and then 5 to 10% goes to the actuators. And what we get is something like this. But of course, these values here, they depend very heavily that what kind of components are chosen to hydraulic system and are we running the hydraulic system with maximum power or some other power, we might have a different efficiency there. So as a designer, these are the values that you can have effect by selecting the correct components to your hydraulic system. And especially so that you make sure that you have enough big pipes so that you don't have too much and enough big valves so that you don't have too much losses in pipes and valves.
Excuse me, I just want to ask, like, in previous lecture, we have some knowledge about the throttle valve and opening valve.
Yes. Yes.
So is the fluid going to opening valve considered as the wasting power?
Yeah, you can think so if you have a look at this circuit here. There is some kind of a pressure relief valve, and if the oil is not able to go in here to the cylinder, the only road it has is to go here. And actually in this circuit, for some reason, there is some two different pressure relief valve. There is already some internal valve inside this hydraulic uh, package here, power package, and then there is an additional pressure relief valve in here. I don't know the reason why there is two of them, but still there is.
Sorry.
Mm-hmm.
So that you said that because as you mentioned in the first of this lecture, like because of the pressure loss that we should have like the pressure relief with like lower value.
Yeah, or I said that you need to put a higher value in this pressure relief valve so that you are able to do the movement that you would like to do, because the pressure what you are getting in this point is different compared to pressure what you have in a cylinder. So if you calculate, you have certain load, you have certain piston diameter, and you calculate that how much pressure I need for this function.
Okay.
It's the pressure in here, but then you need to have more here because you have losses in a way.
Yeah. So like for the first assignment, we didn't take into account the loss, right?
Not so much, yeah.
Yeah.
There was some loss that you took account automatically, even though you didn't know that one, because there are certain elements in fluid sim that takes care of the losses. I can show it to you soon.
Yeah. Okay. Thank you.
And if we talk about this efficiency, like you already calculated this one in this assignment, that it's the output efficiency divided by input efficiency, and in your case, I asked you to calculate this mechanical power, and the input power was this hydraulic power. But in hydraulics, you can also divide this efficiency in two different pieces. You can talk about volumetric efficiency and hydromechanical efficiency. This volumetric efficiency basically means that if you have some leakages in your system, then it's taken account with this term, and this hydromechanical efficiency. For instance, we might have a cylinder or hydraulic pump, and if there is some leakage in a cylinder, it would be seen visible in this efficiency, and all the frictions what happens in the cylinder, they would be in here. Okay, but then a little bit back here.
Sorry, Simo.
Yep.
Would you repeat what it means, the efficiency with these letters, with K, OK, and all this? The other, yes, here, what it means is.
Oh yes, this comes from Finnish language, I'm sorry. It should be, I would say, TOT, meaning total. So this comes from a Finnish word kokonais,
Okay.
which is equal to total.
Okay.
So, sorry.
And the other is the volume, or?
This is volumetric efficiency, meaning this one, and this HM means hydromechanical efficiency.
Okay, okay. Now it's clear, thank you.
Okay, thanks. Okay, but a little bit more about these curves. I told you that you get this information from manufacturer, and I can show you if we go to our course, to Moodle, and we go to hydraulic components sheet, and there are manufacturer catalogs, and if we go to the Bosch Rexroth catalog, and then we want to study valves. Well, in this case, I want to study normal directional valves, so they are called on-off valves here. And still I want to stick here in the directional valves. Okay. And two different main type of directional valves depending on the construction. There are seat valves and spool valves. The spool valves are the most common ones, and let's select this one. Then still we have to make selection whether to study direct operated or pilot operated valve. I want to keep it simple, and I will select this direct operated. Later I will give you a lecture about these valves. I will tell more about what those selections means, but now I just want to show you the data sheet. Directional spool valve, direct operated with solenoid actuation, and then the data sheet. Okay, please open the sheet now. It's here. This is a picture of the valve.